Hello dear friends, make yourselves comfortable. In this video, I will tell you how the comet, or rather the 3I Atlas spacecraft, surprised us again. Believe me, you have something to hear. So please like this video and subscribe, as I try to share the most relevant and expert information with you. Let's start with something appeared in the space between 3I Atlas and Earth, and no one saw it coming until just 2 days earlier. On November 2nd, Russian astronomer Gennady Borisov, the same observer who discovered the second interstellar object ever recorded, detected something new. A comet, but not one that fits comfortably into known categories. This object, designated C2025 and V1 BORISOV, occupies a position that has quickly drawn attention across the astronomical community. As of November 7, it sits in a region of the inner solar system that challenges simple explanation and has fueled intense discussion among both professionals and amateurs. Observers describe a defined, compact nucleus clearly visible in telescopic images. Yet one critical feature is missing: a tail. Comets typically develop long luminous tails as solar radiation heats their icy surfaces, releasing gas and dust that stream away from the sun. That process is what distinguishes a comet from an asteroid. But V1 BORISOV shows none of it, only a bright condensed core, motionless in the darkness, positioned almost exactly along the line connecting 3I Atlas and Earth. It appeared by chance in the precise region of sky where few were looking. Borisov, operating his custom-built half-meter telescope from Crimea, happened to be surveying that area on the night between November 1st and 2. Within hours, confirmation came from other observatories. On November 5th, the Minor Planet Center issued an official circular, and soon 10 observatories independently confirmed the detection. Each reported a faint cometary coma, roughly 1.5 arcseconds across, with a short tail extending 7 arcseconds toward position angles between 250 degree and 260 degree. Its brightness measured around magnitude 12, too dim for the naked eye, but well within reach of professional telescopes. That brightness implies that the comet should have been visible for weeks if anyone had been observing that region, yet no one was. At the time, nearly every telescope was focused on 3I Atlas, the interstellar object dominating observation schedules and press coverage since July. While attention stayed fixed on Atlas, something else slipped quietly into the space between it and our planet. V1 BORISOV made its closest approach to Earth on November 11th, passing at 0.6969 astronomical units, about 103 million kilometers. That distance poses no danger, but it is close enough to invite careful study. From that geometry, any observer, natural or otherwise, would have an ideal vantage point for watching our world. This coincidence has sparked debate far beyond ordinary comet discussions. Some theorists suggest that V1 BORISOV might not be a comet at all, but rather a smaller craft released from 3I Atlas, functioning as a probe. The idea draws on earlier speculation by physicist Avi Loeb, who proposed that interstellar objects could be technological in origin. The timing aligns suspiciously well. Atlas reached perihelion, its closest approach to the Sun, on October 29th. During those days, it was hidden from Earth-based telescopes by solar glare. At precisely that time, Atlas began showing non-gravitational acceleration, movement that gravity alone cannot explain. The Jet Propulsion Laboratory confirmed this in its published data. Such acceleration typically results from the expulsion of material jets of gas and dust, pushing a comet like miniature thrusters. But in this case, no such expulsion was seen. The absence of a debris cloud suggests an alternative mechanism. If Atlas expelled part of itself during perihelion, a fragment or probe, it would have followed a trajectory determined by the velocity and direction of release. Executed at the optimal moment, during the peak of solar gravity, where orbital mechanics favour efficiency, the Oberth effect, that fragment could have been placed precisely along the path between Atlas and Earth, the very location where V1 BORISOV was later found. This hypothesis did not emerge from fringe speculation alone. Orbital dynamics specialists noted that the kinematic data supports such a possibility. When a large object experiences measurable acceleration, the expelled mass must exist somewhere. Physics demands conservation of momentum. Calculations by Loeb estimated that Atlas may have lost 13% of its total mass, roughly 5 billion tons of material, yet telescopes detect no corresponding debris field. Post-perihelion images taken on November 5th show Atlas as a compact light source with no extended tail or cloud. The Arnavis Observatory in Spain and the Virtual Telescope project in Italy both captured this same appearance. A bright, condensed object without the vast dusty envelope that should accompany such mass loss. For comparison, those same instruments imaged Comet Lemon the same day, a typical solar system comet that displayed a textbook tail, long and luminous, pointing directly away from the Sun. Atlas did not. V1 BORISOV's behaviour deepens the mystery. Its perihelion occurs on November 1653 at a distance of 0.46 AU, well within the orbit of Mercury. At that proximity, any ordinary icy nucleus should erupt with intense outgassing, producing a brilliant coma and tail. Instead, observers report minimal visible activity, a small, faint coma, and a short, stubby tail. This suggests one of three possibilities: a composition unusually low in volatile ices, a surface already hardened by previous radiation exposure, or a fundamentally different nature. Orbital data reinforce its peculiarity. V1 BORISOV's eccentricity is 1.0096, identifying it as hyperbolic unbound to the Sun, passing through only once, like Atlas. Its inclination of 112.7 degrees means it moves retrograde opposite the direction of the planet's orbits. At the same time, its path brought it near Earth precisely as 3I Atlas emerged from behind the Sun. Coincidence is possible, but the alignment to interstellar objects, both hyperbolic, both anomalous, one positioned directly between the other, and Earth stretches probability to its limit. The idea that V1 BORISOV might be a probe released by 3I Atlas rests on several lines of reasoning. Each one is weak on its own, but gains strength when viewed together. First, the evidence of mass loss. NASA confirmed non-gravitational acceleration in Atlas, motion that only occurs when an object expels material. Physically, that means at least part of its mass was ejected to conserve momentum. Loeb's estimate of a 13% mass reduction, or about 5 billion tons, comes directly from those measurements. That material has to exist somewhere. Second, images taken after perihelion show no debris cloud. If Atlas had released that much gas and dust, telescopes would detect a broad glowing halo or jet structure. Instead, all observations show a compact, symmetrical nucleus. Nothing indicates widespread ejection. the absence of any visible debris suggests that the lost mass stayed coherent, perhaps as a single body or cluster of bodies rather than a diffuse cloud. Third, the timing and geometry. V1 BORISOV appeared days after Atlas passed perihelion in precisely the region between Atlas and Earth. It has a nucleus but barely any tail, an uncommon profile for an object so close to the Sun. And its discovery was almost accidental, found by Borisov while scanning the sky manually. The probability that an experienced comet hunter just happened to detect the only other interstellar object aligned with Atlas is small. This does not prove intent or design, but the alignment of factors, time, position, and behavior invites further study. Some scientists note that if the object wanted to be noticed, it succeeded. Borisov is credible, his discoveries carefully verified. His observation ensured that V1 Borisov entered official records immediately. Trajectory analysis adds more complexity. When 3I Atlas first entered the solar system, astronomers computed its path using standard gravitational models. Those equations predicted precise positions for each observation window, but as new data arrived, small discrepancies appeared. The comet was not exactly where calculations placed it. The differences were minor at first, a few kilometers across millions, but they grew. By October, as Atlas neared perihelion, the deviation had become too large to dismiss as measurement error. NASA attributed the shift to outgassing, the normal explanation when comets drift. Escaping gas acts like microthrusters, slightly altering trajectory. It's a common effect. Yet for Atlas, that answer creates a contradiction. If enough gas vented to move the comet measurably, we should detect the expelled material. Spectroscopic data would reveal molecular lines from water vapor, carbon monoxide, or dust. Imaging would show the extended coma, but none of that appears. There is acceleration without visible exhaust, cause without observable effect. The question becomes unavoidable. Where did the mass go? If Atlas expelled a substantial portion of itself but produced no detectable debris, then the release must have been directional and controlled. In spacecraft design, the most efficient moment for such a maneuver is perihelion, when velocity peaks and gravitational potential energy converts most effectively to kinetic energy, a principle known as the Oberth effect. A hypothetical intelligent probe would exploit exactly that window, burn or release material at perihelion to alter course or deploy secondary units while hidden in the sun's glare. 4 days after that event, V1 Borisov appeared. Its trajectory lies directly between Atlas and Earth. Correlation is not proof, but physics links the two events cleanly. If Atlas expelled mass purposefully, a compact object like V1 Borisov could follow a projected path leading to its present position. For now, the data show only correlation. To confirm causation, scientists would need direct evidence, spectroscopy identifying artificial compounds, radio emissions, or structural imagery that cannot arise naturally. None exist yet, but patterns persist, and patterns invite hypotheses. The online scientific community has responded intensely. Forums that once focused solely on Atlas now analyze Borisov's orbit, calculating relative vectors and comparing eccentricities. Some users argue for natural coincidence. Others point out that multiple improbable alignments are difficult to dismiss collectively. Professional astronomers, including Borisov himself, remain cautious. He reported his findings formally, avoided speculation, and moved on as procedure demands. His silence has not stopped debate. The deeper question is what happens next. Observatories continue tracking both objects. 3I Atlas is moving outward from the Sun, regaining visibility as it approaches its closest distance to Earth on December 19th. V1 Borisov, on its hyperbolic path, will also remain observable for several weeks before fading beyond reach. During that time, telescopes worldwide will collect light curves, refine trajectories, and analyze spectra. With enough data, astronomers may finally determine whether these objects behave like normal comets or something entirely new. A natural explanation would settle the issue. A solid body with unusual composition or geometry could account for the missing tail and odd brightness patterns. But if continued observation reinforces the anomalies, no visible tail, inconsistent acceleration, unexpected color changes, then the hypothesis of non-natural origin will gain weight. For now, science proceeds cautiously. The evidence supports anomalies but not conclusions. What is certain is that two interstellar objects are currently present in the solar system, an unprecedented event. Both are unbound, both arrived from beyond, and one lies directly between the other and Earth. That alignment alone ensures that the coming months will deliver critical data and perhaps answers to questions that have remained speculation for decades. While the world debates what appeared between 3I Atlas and Earth, another story unfolds behind closed doors, one involving silence, bureaucracy, and withheld data. NASA possesses high-resolution images of 3I Atlas that have not been released to the public. These images were captured by the Mars Reconnaissance Orbiter, MRO, on October 2nd, 3, when Atlas passed within 29 million kilometers of Mars, the closest any interstellar object has ever come to a spacecraft equipped for observation. The MRO's high-rise camera, with a 50-centimeter aperture, achieved a spatial resolution of roughly 30 kilometers per pixel, 3 times sharper than the best image ever taken by the Hubble Space Telescope. Such clarity could reveal surface features, potential jets of gas, or even geometric structures if they existed. Yet as of November 7th, those images remain unseen. The official explanation is procedural. On October 1st, the US federal government entered a shutdown. Funding lapsed, non-essential staff were placed on furlough, and data processing pipelines stopped. According to NASA, the personnel required to calibrate and approve image release are unavailable until operations resume. It is a convenient coincidence. Atlas made its closest pass by Mars on October 3rd, 2 days after the shutdown began. The world's best data set on an interstellar object now sits idle, inaccessible, while public debate intensifies. Astrophysicist Avi Loeb criticized this situation in a November 1st post, calling it an example not of extraterrestrial mystery, but of terrestrial dysfunction. He argued that science should not be held hostage to politics, noting that time-sensitive data loses value every day it remains unreleased. He's right about timing. Atlas continues to move outward from the Sun, dimming rapidly. Planning new observations requires precise knowledge of its activity level and structure, information that the high-rise images could provide. Without them, astronomers must allocate telescope time blindly, risking redundant or misaligned observations. NASA's silence contrasts sharply with other missions unaffected by the shutdown. The James Webb Space Telescope continues to publish imagery. Hubble, Europa Clipper, and even the Mars rovers transmit data normally. Yet the single dataset capable of clarifying Atlas's nature remains locked away. Some have begun to question whether bureaucracy is the real reason. On October 31st, Congresswoman Anna Paulina Luna of Florida sent a formal letter to NASA's acting administrator, Sean Duffy, requesting immediate release of all observational data on 3I Atlas, including high-rise imagery. Luna emphasized that the information has clear scientific and national security significance, especially given the object's unusual properties and proximity. Her letter followed consultation with Loeb, who, unable to reach NASA directly, sought political intervention after a suggestion from public interviews. Luna's tone was firm. The delay is unacceptable. Transparency serves public interest better than silence. On November 5th, she posted an update on social media stating that NASA had agreed to release the data once the government reopens, but not before. Unfortunately, due to bureaucratic reasons, her statement read, "They cannot." That phrasing, bureaucratic reasons, feels inadequate given the stakes. These are not routine administrative documents. They are the clearest observations ever made of a confirmed interstellar object. Meanwhile, outside the United States, other agencies proceed. The European Space Agency, ESA, attempted its own imaging of Atlas during the Mars flyby, using both Mars Express and the ExoMars Trace Gas Orbiter. From 488 frames captured, ESA released only 2, showing Atlas as a faint white dot against space. The remaining 486 images have not been published or explained. China's National Space Administration, CNSA, took a different approach. On November 6th, it released several images captured by the Tianwen-1 Mars orbiter. Those photographs show a nucleus surrounded by a coma between 5,000 and 10,000 kilometers across. Tianwen-1's high-resolution camera, with a 38.7 centimeter mirror, is smaller than high-rises, but still powerful enough to reveal major features. The CNSA acknowledged the technical difficulty of imaging an object 10,000 to 100,000 times fainter than the Martian surface. Yet they succeeded and shared the data openly. NASA, with better optics and greater resources, remains silent. The longer the delay, the weaker the shutdown justification appears. The high-rise data could answer direct scientific questions. Is 3I Atlas a single solid nucleus or a cluster of fragments? Does its surface show jets or localized activity consistent with outgassing? Are there geometric features inconsistent with natural formation? These are not speculative curiosities. They define whether the object behaves like a comet or something engineered. If Atlas lost 5 billion tons of material, as Loeb's calculations imply, the resulting debris should form a diffuse halo of dust, bright enough for high-rise to detect. If that halo is absent, the anomaly deepens. NASA officials know this. Someone has already seen those images internally. The data have been downloaded, calibrated, and stored on secure servers. The choice not to release them may be as much about optics, political, not optical, as about policy. Loeb himself remains cautious. He wrote that the delay is probably a sign of terrestrial stupidity rather than extraterrestrial intelligence. But his wording left room for interpretation. probably acknowledges uncertainty. That while incompetence is the simplest explanation, suppression cannot be ruled out. If the high-rise data reveals surface geometry inconsistent with natural objects, regular edges, smooth planes, or patterns of light reflection, NASA would face an extraordinary problem. It has already publicly dismissed the idea that Atlas is anything but a comet. Releasing contradictory evidence would invite immediate scrutiny and potential ridicule. Easier, perhaps, to postpone, to wait until attention fades. But time is running out. Atlas approaches its closest distance to Earth on December 19th, when every major observatory will be watching. The absence of high-resolution Mars data leaves researchers unprepared. They cannot refine models, plan exposure times, or coordinate follow-ups with precision. Loeb summarized the situation plainly. We should not hold science hostage to politics. Yet politics hold the keys to the servers where the images sit, and until they are opened, the clearest view of an interstellar visitor remains unseen. On November 5th, 2 observatories published new images of 3I Atlas. What they revealed or failed to reveal has become a central problem for astronomers who maintain that the object is a natural comet. The Arnavis Observatory in Spain and the Virtual Telescope project in Italy both captured Atlas under difficult conditions. Despite bright moonlight and the object's low altitude near the horizon, the images were clear enough for analysis. Each showed the same thing: a compact, diffuse sphere of light with a faint surrounding glow, but no visible tail. Comets almost always display tails when approaching the Sun. The process is well understood. As solar radiation heats their icy surfaces, volatile materials sublimate, ejecting gas and dust that sunlight then pushes outward, forming a bright streamer millions of kilometers long. The direction of the tail is predictable. It always points away from the Sun. Atlas does not follow this rule. In the Arnavis images, the area where a tail should appear shows nothing, no brightening, no extension, no trace of structure. The team even marked the anti-solar direction with an arrow, confirming that the tail should have been obvious under those viewing conditions. To validate their methods, the same telescopes imaged Comet Lemon on November 3rd, just 2 days earlier. Lemon produced the expected bright, elongated tail pointing directly away from the Sun, perfectly consistent with standard cometary physics. The equipment and observers worked as expected. The difference lies entirely in the object. For comets, tail formation is not optional. It is a direct consequence of heating and outgassing. The closer to the Sun, the stronger the effect. Atlas reached perihelion on October 29th at 1.4 astronomical units, closer than Mars, farther than Earth, well within the range where active outgassing occurs. From the measured non-gravitational acceleration, Loeb calculated that the comet must have lost at least 13% of its total mass over 5 billion tons of material. That much ejected gas and dust should have formed an immense cloud, easily visible even through moderate telescopes. Instead, the post-perihelion images show a coma only a few thousand kilometers across, comparable to its appearance months earlier when activity should have been far lower. Physics leaves little room for ambiguity. 5 billion tons of gas and dust cannot simply disappear. Those particles reflect sunlight. They would make the object shine brightly and develop a large, distinct tail. Yet telescopes detect none of it. This contradiction-clear acceleration without a visible debris field has been labelled by Loeb as the 10th anomaly of 3I Atlas. The comet behaves as if it expelled mass on a catastrophic scale but left no observable trace. The effect is real, the cause is missing. Possible explanations exist, but each faces problems. The first is fragmentation, the idea that Atlas broke apart, releasing large pieces rather than fine dust. But such fragmentation events are dramatic. They produce chaotic shapes, bright plumes, and complex dust structures. Hubble has recorded many examples, and none resemble Atlas's calm, symmetrical profile. The second explanation is directed outgassing. Perhaps the comet vented gas through a specific jet aimed away from our line of sight. This could produce thrust without a visible tail. However, directed outgassing requires focused vents natural nozzles on the surface that channel material in one direction. Random fractures cannot sustain that precision. Spacecraft engines can. The third hypothesis is that the expelled material remained coherent travelling as one dense body instead of dispersing. That interpretation aligns with the idea that Atlas released a compact object, not dust. Such a release would account for both the acceleration and the missing debris field. None of these explanations fit comfortably within the framework of a normal comet. Each assumes behavior rarely observed or entirely theoretical. Some researchers have attempted geometric arguments. Maybe the tail exists, but is oriented in a way that makes it invisible from Earth. Tails can appear shortened when viewed edge-on, a known optical effect. But geometry cannot explain complete absence. By November 5th, Atlas had moved well beyond solar conjunction, giving Earth a favourable viewing angle. The same telescopes that saw Lemon's tail under identical geometry would have seen Atlas's if it were there. The conclusion is unavoidable. Either our understanding of comet physics is incomplete, or Atlas is not behaving as a comet should. Loeb's compilation of anomalies underscores this problem. The missing tail joins others already identified retrograde trajectory, unexpected blue coloration, non-gravitational acceleration, and fine-tuned orbital alignment. Each individual discrepancy might be tolerable. Together they form a coherent pattern that challenges the natural interpretation. For scientists, the missing tail is more than a curiosity. It is an observational fact that defies established models. Comets, by definition, produce visible tails when they lose mass. When a body shows mass loss without one, classification must be reconsidered. Upcoming observations, especially those scheduled for December 19th, will be decisive. If the tail remains absent despite continued solar heating, the anomaly can no longer be dismissed as geometry or temporary inactivity. It would imply a fundamentally different mechanism of motion, possibly controlled propulsion, rather than natural outgassing. For now, the data remain consistent in one respect. Atlas continues to defy expectations. It accelerates without exhaust, brightens and dims irregularly, and maintains a smooth profile where turbulence should dominate. Whether this is due to unknown natural processes or deliberate control is a question that science must confront with open evidence, not assumptions. Colour in astronomy is never just visual. It carries physical meaning. It reveals temperature, composition, and the processes shaping an object's light. When an interstellar object changes colour, physics demands an explanation. 3I Atlas has changed colour 3 times since its discovery. each shift occurring near critical points in its orbit. The most recent transformation, its transition to a distinct blue hue, appeared during and immediately after perihelion, when the object was closest to the Sun. This is not artistic interpretation or false color imaging. The blue tone is evident in calibrated photometric data from multiple spacecraft. Blue light corresponds to shorter wavelengths and higher photon energies than the reddish glow typical of cometary dust. That shift alone suggests a process far more energetic than simple reflection. In natural comets, color changes gradually as distance from the Sun decreases. Different ices vaporize at different temperatures, releasing gases that emit characteristic colors: greens from diatomic carbon, reds from oxygen, yellows from sodium. But these transitions are smooth, predictable, and limited in range. Atlas's color shifts are abrupt and extreme. During perihelion, when Earth-based telescopes were blinded by the Sun's glare, spacecraft monitoring from other angles recorded the sudden brightening and bluing of the object. The analysis in a recent preprint describes Atlas as bluer than the Sun itself. That comparison matters. Sunlight reflected by dust should roughly match the Sun's color temperature or appear slightly redder due to scattering. Becoming bluer implies an additional light source or emission process. Astrophysicist Avi Loeb addressed this directly. He noted that for a natural comet, such a blue hue is very surprising because dust reflection tends to redden rather than shift toward shorter wavelengths. In other words, Atlas appears to emit rather than merely reflect light. There are two broad categories of explanation. The first is natural, emission from ionized carbon monoxide, CO+. When ultraviolet radiation from the Sun strips electrons from CO molecules, the recombination process produces blue emission lines. This phenomenon is known in other contexts. Some comets exhibit faint blue glows when CO+ dominates their spectra. For this explanation to fit Atlas, the comet would have needed to release enormous amounts of carbon monoxide gas during perihelion enough to overwhelm other spectral components. That would require massive outgassing, but the images show no large coma or tail, contradicting that scenario. If the object vented CO on such a scale, telescopes would detect a surrounding cloud tens of thousands of kilometers wide. None has been observed. The second explanation is technological. The blue color could arise from artificial illumination or propulsion. High-temperature engines, plasma discharges, or ion drives often produce blue light due to the acceleration of charged particles. Even terrestrial examples, arc welding, plasma thrusters, nuclear Cherenkov radiation share this spectral signature. If Atlas contains internal power systems that activated near perihelion, the blue emission might represent engine exhaust, electrical discharge, or operational lighting. The timing fits perfectly. Perihelion provides maximum solar energy for systems powered by sunlight, and it is also the most efficient moment for propulsion maneuvers using the Oberth effect. During perihelion, a small burst of thrust yields a large change in trajectory. If Atlas executed such a maneuver, the non-gravitational acceleration detected by NASA would make sense as active propulsion rather than random gas release. In that case, the blue glow would be the visible byproduct of energy use, hot plasma radiating at short wavelengths. The observed rapid brightening by a factor of 5 in the green spectral band near 0.46 micrometers supports this possibility. Natural comets brighten steadily as they approach the Sun, following predictable curves based on distance and solar flux. A sudden increase indicates an abrupt process. Something switched on. No known natural mechanism matches that behavior cleanly. Sudden cracks exposing fresh ice can cause brief brightening, but it fades quickly as dust settles. Collisions can also increase brightness, but the likelihood of an impact exactly during perihelion is negligible. Artificial systems, on the other hand, regularly show step-like activation patterns. Engines firing, instruments powering up, or energy systems engaging. Still, this remains hypothesis, not proof. The data show what happened, the color change, the brightening, the acceleration, but not why. To prove a technological cause would require direct spectral lines of industrial materials or specific radiation signatures. Current observations stop short of that. Yet the convergence of anomalies is difficult to ignore. Atlas shows acceleration without exhaust, mass loss without debris, and now color change without a natural driver. Each inconsistency can be debated individually. Together, they outline a pattern. Loeb presents this carefully. He does not declare Atlas artificial, but argues that excluding the possibility is unscientific. Evidence must guide interpretation, not habit. He notes that extraordinary claims require extraordinary evidence, but also that evidence requires openness to extraordinary possibilities. Institutional science tends to favor the familiar. Suggesting that an interstellar object might be technological invites skepticism, funding risk, and professional ridicule. Yet data remain indifferent to reputation. The blue emission is real. It exists in measured spectra. The question is what physical process can produce it without accompanying gas emissions or dust scattering. As Loeb summarized, if Atlas emitted blue light due to ionized carbon monoxide, then a massive gas cloud should accompany it. If no such cloud exists, another mechanism must be responsible. Each missing element tail, debris, expected outgassing reinforces the others. In the end, the blue color becomes more than a curiosity. It is a diagnostic clue, a signature of energy, possibly of control. Whether natural or artificial, it indicates a process that standard comet models cannot easily reproduce. The coming weeks of observation will test every interpretation. Spectroscopy may detect faint molecular lines revealing chemical composition. Photometry will trace brightness over time, confirming whether the blue hue persists or fades. Each measurement will narrow the range of explanations. Until then, the mystery stands. A visitor from beyond the solar system, accelerating without visible thrust, glowing blue in the sun's light, and breaking the known rules of cometary behavior. NASA has now confirmed what earlier calculations suggested. 3I. Atlas is accelerating in ways that gravity alone cannot explain. The measurement is statistically solid 3.7 standard deviations above background noise. In physics, that threshold distinguishes random fluctuation from genuine signal. This is real motion, not instrumentation error or numerical drift. Astronomers recorded Atlas's position repeatedly over several months, comparing it with predictions based on gravitational models refined over centuries. The difference between the expected and the observed path increased with time, producing a measurable offset that could no longer be attributed to uncertainty. Such deviations are not unprecedented. Many comets experience non-gravitational acceleration when volatile gases escape from their surfaces. The escaping material acts like a weak rocket exhaust, nudging the nucleus slightly. From the size of that deviation, scientists can estimate how much material was lost and how strongly the venting acted. For Atlas, the required outgassing would have been enormous. Loeb's team applied standard momentum conservation equations. If the comet accelerated as measured, and if the escaping gases reached typical velocities for sublimated ice, the implied mass loss equals roughly 13% of the total body, about 5 billion tons. That is not a minor venting episode. It is a catastrophic event. 5 billion tons of expelled material should create a brilliant cloud visible across the solar system. It would scatter sunlight, form a massive coma, and dominate telescope images for weeks. Yet the November 5th observations show only a compact nucleus with a faint glow. The expected debris is missing. This paradox defines the problem. Acceleration is confirmed, but its physical cause is invisible. Some possibilities can be ruled out. Measurement error is unlikely given independent confirmation by multiple observatories and the Jet Propulsion Laboratory. The mathematics of momentum conservation are not in dispute. That leaves only the nature of the expelled mass itself. If the ejection were directional, not diffuse, the visible signature could be smaller. A strong jet venting from a localized region could produce thrust without forming a wide tail. However, directed jets are typically obvious bright streamers captured in comet imagery. Atlas shows none. Another possibility is a brief intense outburst during perihelion. A sudden collapse of surface layers or internal pressure release could have generated a momentary plume that produced acceleration but dispersed before observations resumed. Such events do occur on other comets, but they leave persistent trails along the orbital path. No such trails have been detected. The remaining explanation fits the data, but challenges assumptions. The mass loss did not behave like gas or dust at all. It stayed cohesive perhaps as a single compact object ejected deliberately. If so, the measured acceleration would correspond to propulsion or deployment rather than natural venting. This interpretation aligns with orbital timing. The greatest deviation occurred precisely near perihelion, when any maneuver, natural or artificial, would be most efficient under the Oberth effect. 4 days later, V1 BORISOV appeared between Atlas and Earth. From an engineering perspective, this sequence makes sense. A vehicle performing a perihelion burn could release a smaller craft onto a trajectory intersecting Earth's orbital region while continuing outward on its own hyperbolic path. From an astronomical standpoint, it is a chain of coincidences that demand scrutiny. NASA has offered no alternative explanation beyond the standard outgassing model, despite the absence of visual evidence. Their official line is cautious. Atlas behaves like a comet. Yet a comet that accelerates without releasing gas contradicts the very mechanism invoked to explain it. 3 possibilities remain. The acceleration measurement is wrong. That would require multiple observatories to have made identical errors, which is improbable. The momentum-based mass loss calculation is flawed, implying a misunderstanding of fundamental physics. That is also unlikely. The expelled mass exists but does not manifest as ordinary debris. If the third case is true, the simplest natural analogy fails. The event looks less like sublimation and more like propulsion. For scientists, admitting that possibility is uncomfortable but necessary. Data should determine theory, not the reverse. The acceleration is observed, the tail is absent. The physics either must be revised or the classification reconsidered. Future observations are critical. On December 19th, Atlas will pass within 1.8 astronomical units of Earth, its nearest approach and the last opportunity for high-precision study before it leaves the solar system forever. Spectroscopy, light curve tracking, and radar ranging may help determine whether the acceleration continues or fades. A steady, directed change would support active control. A gradual decay would favor natural venting. Until those measurements arrive, the evidence remains balanced but puzzling. A confirmed acceleration without visible exhaust challenges not just assumptions about one comet, but about the limits of what interstellar visitors might be. The date December 19th marks a convergence that astronomers have anticipated for months. On that day, 3I Atlas will reach its closest approach to Earth, coming within 1.8 astronomical units. Though still far about 270 million kilometers, this distance allows high-precision observation from both ground-based telescopes and orbiting instruments. For the scientific community, the event is an opportunity to test every assumption made since the object's discovery. Atlas is leaving the inner solar system, and the data gathered now will be the last before it disappears forever into interstellar space. Dozens of observatories have scheduled coordinated observation windows. The European Southern Observatory plans simultaneous tracking through its Very Large Telescope in Chile and the La Silla facility further north. In the United States, Lowell Observatory, Mount Lemmon Survey, and the Subaru Telescope in Hawaii will each dedicate several nights to continuous monitoring. Space-based missions will participate as well. The James Webb Space Telescope, JWST, will attempt mid-infrared spectroscopy to identify any molecular emissions from residual gases. The Hubble Space Telescope will image the optical coma and check for structural changes. Even the Gaia satellite, primarily a stellar survey mission, will collect photometric readings to refine the orbit. The campaign's goals are straightforward. Measure whether Atlas's non-gravitational acceleration continues. Detect any new outgassing or tail formation. Determine the composition through spectroscopy. Search for fragmentation or secondary objects. Each result carries implications. If acceleration persists while the comet remains inactive, the propulsion hypothesis gains credibility. If a tail finally appears, the anomaly resolves naturally. Either outcome advances understanding. Parallel attention now turns to V1 BORISOV, the smaller body discovered between Atlas and Earth. Its own perihelion occurred on November 16th, and it will remain observable into January. Because its orbital plane intersects Earth's, its apparent motion across the sky provides a convenient reference for comparative study. Several teams intend to analyze both objects simultaneously, comparing spectral features and polarization data. If the two share identical compositions, a common origin becomes likely. If not, coincidence may still explain the alignment. The Atacama Large Millimeter Array, ALMA, will target possible carbon monoxide lines near 230 GHz, the signature frequency for cometary outgassing. Any detection would indicate ongoing sublimation. Conversely, An absence of emission combined with sustained acceleration would again suggest a non-volatile mechanism. Meanwhile, independent observers, amateurs and professionals alike, have organized a global effort known informally as the Atlas Watch Network. Its participants share photometric data nightly, synchronizing observations through open databases. The collective aim is redundancy, to ensure that every variation in brightness or motion is documented from multiple vantage points. NASA's Jet Propulsion Laboratory has updated its orbital model based on the latest tracking data. The new solution still classifies Atlas as hyperbolic, with an eccentricity of 1.078, confirming that it will not return. Its velocity relative to the Sun now exceeds 42 kilometers per second, the threshold for solar escape. The object is on its way out, carrying with it whatever clues it holds about its origin. The approaching observation window also carries logistical tension. Because of the earlier government shutdown, NASA's high-rise images from October remain unreleased. Without them, astronomers lack the high-resolution baseline that would help interpret new data. Several institutions have requested temporary access under scientific emergency provisions, but approval remains pending. The absence of those images creates gaps in modelling. Scientists can track motion precisely, but cannot confirm surface structure or albedo variation. These details are essential for interpreting light curve changes expected around December 19th. If brightness fluctuates periodically, it could indicate rotation, shape irregularities, or reflective surfaces, each clue narrowing possibilities. For now, models remain split. One class treats Atlas as a volatile poor interstellar comet, a dense body of refractory materials that resists outgassing. The other treats it as an engineered object, using energy rather than sublimation to alter course. Both explanations accommodate the observed acceleration, but their physical mechanisms differ radically. ESA scientist Marco Langbroek summarized the dilemma in a recent statement. Every measurement fits within the equations of motion. What we cannot fit is the process driving them. That sentiment reflects the broader tone across the field, curiosity tempered by caution. No one claims proof of artificial design, yet few dismiss the anomalies outright. The data compel engagement, not avoidance. If December 19th passes without incident, the next challenge will be synthesis. Hundreds of terabytes of spectral and photometric data will require months of calibration and analysis. By mid-2026, researchers hope to publish consolidated results, mass estimates, compositional spectra, and final orbital reconstructions. Whatever the outcome, the event will reshape how interstellar visitors are studied. Atlas and Borisov demonstrate that such objects are not once-in-a-lifetime phenomena. They may arrive more often than previously thought. The challenge lies in detecting and understanding them before they vanish into deep space. For the public, December 19th will likely pass quietly, no visible spectacle, no dramatic sky show. But for those behind the instruments, it represents a decisive moment, either confirmation of standard physics or the beginning of something entirely new. If December 19th passes without surprises, the story of 3I Atlas will still mark a turning point in the study of interstellar objects. Even a negative result. No new acceleration, no unusual emissions will refine our understanding of what such visitors can be. Science often advances through anomalies that eventually prove ordinary, yet sometimes the anomalies remain. Atlas has already rewritten several assumptions. It shows that interstellar bodies can approach close enough for detailed study and that they may not behave like typical comets. Whether natural or not, Atlas expands the boundary of what we must be ready to observe. The next time something crosses into the solar system from interstellar space, instruments and observers will respond faster, guided by lessons from this case. For now, researchers prepare to interpret the December data with cautious precision. Photometric curves will reveal rotational dynamics, how fast Atlas spins, whether it tumbles or maintains stable orientation. Spectroscopy will check for volatile elements such as water, methane, or carbon monoxide. If none are detected, the argument for a non-cometary structure will strengthen. Infrared measurements will trace heat distribution across the surface. A uniform thermal profile would imply metallic or composite materials capable of conducting heat efficiently. Irregular patches would point toward a more porous, natural composition. Radar echoes from deep space antennas may even detect microsecond-level variations indicating geometric edges or smooth planes patterns rarely found in purely natural bodies. By early 2026, when data calibration is complete, astronomers expect to publish a definitive model describing Atlas's trajectory and composition. Whether that report concludes with natural or unknown, it will stand as one of the most detailed case studies ever conducted on an interstellar visitor. Meanwhile, public curiosity remains high. Forums and news outlets continue to speculate, often amplifying theories far beyond evidence. For scientists, managing that gap between data and interpretation has become part of the job. They cannot stop conjecture, but they can ensure that facts remain accessible. Avi Loeb, whose hypotheses helped ignite interest, remains at the center of debate. He has neither claimed nor dismissed artificial origin, instead maintaining that the possibility deserves investigation. His position is unpopular among conservative peers, but consistent with scientific logic. An explanation that fits all data should be preferred, regardless of how unconventional it seems. In that sense, Atlas functions as a stress test, not only for observational technology, but for scientific culture itself. It measures how willing experts are to question established models when faced with data that do not conform. For the moment, institutional caution prevails. NASA and ESA both emphasize that cometary activity can vary widely and that Atlas remains within the outer boundaries of natural behavior. Yet each new observation erodes that comfort slightly. An object that accelerates without visible exhaust, changes color without known chemistry, and aligns precisely with another interstellar body demands more than routine explanation. If December 19th brings no new data to resolve these contradictions, uncertainty will persist. But that uncertainty itself is valuable. It keeps attention focused and ensures that future missions are designed with broader expectations. Already, several proposals have emerged for interstellar intercept missions. Spacecraft intended to pursue and study future visitors up close. The concept is simple in theory, difficult in practice. Detect an incoming interstellar object early, launch a probe fast enough to match its trajectory, and gather direct samples or imagery. For Atlas, it is already too late. By the time such a mission could launch, the object will be millions of kilometers beyond reach. But the planning has begun. The European Space Agency and several private research groups have proposed Project Lyra, a theoretical study exploring how a spacecraft could intercept the next interstellar visitor using existing propulsion technology. Atlas's anomalies have revived that effort. If a similar object appears again, especially one entering the inner solar system, humanity may not have to watch it pass in silence. Beyond technical challenges, Atlas reminds us that curiosity itself remains the driving force of discovery. Whether the answer proves mundane or extraordinary, the process of seeking it strengthens both science and perspective. When the data from December 19th arrive, they will either confirm a standard comet model or establish a new category of interstellar phenomena. In either case, the event will enter textbooks. The first time an interstellar object was tracked from approach through departure, with every anomaly documented in real time. In a broader view, the Atlas episode demonstrates how fragile certainty can be. Astronomy once assumed that the solar system was isolated, its comets and asteroids native. Now we know that interstellar visitors cross our path regularly, carrying material and information from beyond our origin. Each one is a messenger, not in a poetic sense, but in a physical one. They bring evidence of the chemistry, structure, and motion of distant planetary systems. Atlas and Borisov may both be natural wanderers, remnants of distant stellar formations, or they may represent something far rarer signs of activity beyond natural processes. Either interpretation changes how we look at the sky. As December's observations unfold, scientists continue to prepare for either outcome. A silent object drifting outward will confirm stability. A signal, reflection anomaly, or continued acceleration will ignite new investigation. Both paths lead forward. In the end, the value of 3i Atlas lies not in what it is, but in what it forces us to confront: the limits of knowledge, the boundaries of assumption, and the responsibility to follow evidence wherever it leads. By late February 2026, 3i Atlas was already beyond the range of most optical telescopes. Its apparent magnitude dropped below 22, leaving only the largest observatories and deep space instruments able to track it. The final confirmed observation came from the Subaru telescope on Mauna Kea on February 14th, showing a faint point of light moving steadily toward the constellation Perseus. After that, Atlas became statistically indistinguishable from background stars. For the first time in recorded history, humanity had followed an interstellar object continuously from entry to exit. The accumulated dataset now fills several terabytes: raw images, spectra, radar returns, and telemetry logs from dozens of institutions. Together, they form the most detailed archive ever assembled on an object that came from outside our solar system. The first round of results appeared in early May 2026, published jointly by the International Astronomical Union and the European Southern Observatory. The findings confirmed most of the earlier anomalies but added nuance. Atlas's non-gravitational acceleration persisted longer than expected, slowly tapering off as it left the Sun's gravitational influence. The total deviation from a purely Newtonian trajectory amounted to 0.0042 astronomical units per year, a measurable but small drift. Spectroscopic analysis from JWST revealed a flat reflectance curve, almost featureless across visible and infrared wavelengths. That is unusual. Natural comets show absorption bands associated with silicates, hydrocarbons, or water ice. Atlas did not. Its albedo was low, around 0.06, similar to dark carbonaceous asteroids, yet its infrared emissivity suggested a smoother surface than any known cometary nucleus. The absence of volatile lines, no detectable H2O, CO, or CO2, implied that Atlas contained little to no surface ice. If it began as a comet, it had already lost its volatile inventory long before entering the solar system. However, the dataset also revealed periodic brightness modulation every 11.3 hours, consistent with rotation. The amplitude of the variation, about 0.2 magnitudes, suggests a moderately elongated shape, perhaps 2.5 by 1.2 kilometers. The orientation remained stable throughout observation, indicating either a strong internal structure or active stabilization. The Goldstone Solar System radar achieved brief contact on December 23, 2025, capturing radar echoes at 8560 MHz. The return signal was faint but distinct. Its delay Doppler profile indicated a smooth convex surface, lacking the rough scattering typical of porous, icy bodies. Polarimetric analysis reinforced that conclusion. The degree of linear polarization was 8%, significantly lower than the 15 to 20% range typical for dusty comets. A low polarization implies either metallic surface texture or consolidated rock without loose particles. While this alone does not suggest artificiality, it places Atlas in a unique physical category, an interstellar body with the radar characteristics of a solid asteroid, but the orbit of a hyperbolic comet. By mid-2026, the community divided into three interpretive camps. The erosion model. This group argues that Atlas is a desiccated fragment from a distant planetary system, once an icy comet that lost its volatiles during previous stellar encounters. The smoothness and low polarization result from radiation processing over millions of years. The composite model. Others propose that Atlas is not monolithic, but an agglomerate of high-density material bound by internal cohesion. That could explain its stability and weak thermal signature. The technological model. A minority view, supported by Loeb and several independent researchers, posits that Atlas may be a remnant or artifact of artificial origin, perhaps a derelict probe or sail. This hypothesis rests not on proof, but on the accumulation of unexplained consistencies, directed acceleration, absence of exhaust, and unchanging surface reflectance. Each model accounts for some observations, but leaves others unresolved. No single explanation yet reconciles all available data. Observations of V1 BORISOV, the smaller object between Atlas and Earth, ended in January 2026. Its trajectory confirmed that it too follows a hyperbolic path, but with slightly lower velocity. Spectroscopy revealed faint traces of magnesium and silicon, but still no gas emissions. Its color index matched Atlas almost exactly. This correlation revived discussion about shared origin. If Borisov was expelled from Atlas during perihelion, its trajectory and composition should align, and they do, within measurement error. Yet statistical probability remains contested. Random coincidence cannot be entirely ruled out. By spring 2026, public interest had grown into organized inquiry. Multiple Freedom of Information requests targeted NASA's unreleased HiRISE dataset from October 2025. After political pressure, the agency released 12 calibrated frames on April 7, 2026. The images show a compact, symmetrical object roughly 2.5 kilometers long with a reflectivity pattern consistent with metal-rich rock. There are no visible craters, vents or jets. In 3 frames, a bright point appears adjacent to the main body, possibly a detached fragment, possibly artifact noise. The release reignited debate. Commentators called it the quietest revelation of the decade. Official NASA statements described the images as consistent with a naturally eroded object. Still, questions persisted. Why were the data withheld for 5 months? Why were only 12 of over 200 frames published? In response, the National Academies of Sciences formed a working group titled Interstellar Object Task Force, IOTF, tasked with standardizing observation protocols and recommending mission concepts for future encounters. Atlas's passage transformed planetary science in measurable ways. Funding priorities shifted. New grants now emphasize interstellar object early detection and rapid response observation networks. The Vera C. Rubin Observatory, expected to begin full operations in 2027, will be the first facility capable of discovering such objects weeks, not months, before perihelion. Additionally, the Project Lyra Consortium revived its feasibility studies for high-velocity intercept missions. Their latest proposal envisions using a solar thermal propulsion system capable of 3 AU-year acceleration, allowing pursuit of future visitors within a decade of detection. Loeb's group at Harvard has also launched the Galileo project, dedicated to systematic searches for interstellar artifacts. Their first phase focuses on reanalyzing archived data from both Atlas and Borisov, combining spectroscopy, radar, and machine learning models to identify non-random patterns. Beyond technical results, Atlas left a cultural imprint. It reintroduced humility into modern astronomy, a reminder that even with advanced instruments, some questions remain open. The case demonstrates how observation, skepticism, and imagination can coexist without conflict. Each unexplained anomaly becomes not an embarrassment, but an invitation to refine understanding. The line between known and unknown shifts, revealing new ground for curiosity. The scientific consensus remains cautious. Atlas is most likely natural, though natural may describe a broader range of phenomena than previously thought. Objects like it could be ancient, hardened fragments from distant systems, or relics of stellar processes we do not yet understand. But the possibility, however small, that it might be otherwise continues to drive inquiry. As Loeb wrote in his closing report, we cannot choose which evidence to confront. We can only decide whether to look away. Atlas is gone now, receding into the dark between stars. But it left behind something measurable: data, debate, and a renewed sense of scale. It reminded us that even in silence, the universe speaks, and that sometimes the most unsettling discoveries are the ones that say nothing at all. By mid-2026, Atlas was only a memory measured in data. Its signal faded below the noise floor of deep space receivers, and attempts to reacquire it through long baseline arrays yielded nothing but background static. For astronomers, that silence marked both an ending and a beginning. The study of interstellar objects, ISOs, has now become a formal field, defined not by speculation but by protocol. The International Astronomical Union has created a dedicated classification system. Each confirmed visitor will now carry the prefix I, followed by its year of detection. Atlas 3I Chalk 2025 V1 stands as the third confirmed object of interstellar origin after Oumuamua and 2I Borisov. The collective lessons from these three encounters outline a new branch of planetary science. They show that the space between stars is not empty but populated by relics of other worlds, travelling through the galaxy on open orbits. Their chemistry and motion encode the histories of their parent systems, just as meteorites preserve the record of ours. In this light, Atlas becomes a benchmark case. It demonstrated both the limits and the potential of current observation. Despite global cooperation, the scientific community could not capture unambiguous proof of its composition or origin. Yet the coordination between observatories, data pipelines, and independent analysts was unprecedented. The new protocols adopted after Atlas are now called the Rapid ISO Response Framework. Under this system, when a transient hyperbolic object is first detected, automated alerts trigger telescope scheduling across multiple hemispheres within hours. Spectroscopy, photometry, and radar tracking begin simultaneously, ensuring that no early-stage data is lost. This framework is the direct result of lessons learned from Atlas's brief, unpredictable behavior. The theoretical implications extend beyond astronomy. Astrophysicists are re-examining models of stellar system formation and gravitational ejection. Atlas's velocity vector aligned with the galactic plane suggests it may have originated near the Carina-Sagittarius arm, roughly 4,000 light-years from the Sun. If true, it travelled for tens of millions of years before its short encounter with our system. That distance alone challenges assumptions about material durability in interstellar space. Any natural body surviving such exposure must be extraordinarily strong or protected by a dense, radiation-resistant crust. Laboratory experiments have begun replicating those conditions using ion irradiation on carbon silicate composites. The results show that surface vitrification, a natural glass-like coating, can indeed suppress outgassing and explain Atlas's smooth reflectance. Still, some data remain inconsistent. The low polarization, flat spectrum, and absence of typical cometary absorption bands defy easy categorization. It is possible that future detections will reveal similar patterns, making Atlas less exceptional. Or it may remain unique, a statistical outlier that defines the edge of what nature allows. By late 2026, major agencies adjusted their exploration priorities. NASA's Interstellar Probe program, once theoretical, gained active funding for feasibility studies. The concept calls for a nuclear electric spacecraft capable of reaching 100 astronomical units within 25 years, carrying instruments specifically tuned for ISO detection and rendezvous. ESA's Comet Interceptor mission, originally scheduled for 2029, has been modified to include contingency protocols for hyperbolic targets. The spacecraft will remain in a waiting orbit at the Sun-Earth L2 point, ready to redirect toward any newly detected interstellar body. In parallel, the Chinese National Space Administration announced its own plan, a twin-probe system using high-energy solar slingshots to pursue future ISOs. These initiatives reflect an emerging consensus that understanding interstellar visitors is not an optional curiosity, but a strategic scientific priority. Within the scientific community, Atlas has also prompted introspection. Many researchers acknowledge that early discussion around its anomalies. Blue coloration, unexplained acceleration, lack of tail, was dismissed too quickly or handled defensively. Peer review traditionally protects rigor, but in this case, it may have suppressed open inquiry. Post-Atlas conferences now include sessions on epistemic humility, the recognition that dismissal of uncomfortable data can slow progress as effectively as error. At Harvard, Loeb's team continues to analyze archival data under the Galileo Project umbrella. Their position remains unchanged. Atlas may be natural, but the possibility of technological origin should remain within legitimate scientific discourse. That statement, once controversial, now appears in official symposium proceedings. Astronomers expect that more interstellar objects will follow. With modern survey telescopes reaching deeper magnitude limits, detection rates could rise to several per decade. Most will likely be inert, inactive rocks drifting silently through the void. But every new detection will test the Atlas paradigm. Will it accelerate, emit, fragment, or behave like nothing seen before? The next step is not simply observation, but interaction. Several mission studies now include concepts for fast flyby encounters, laser communication beacons, and even sample return possibilities using magnetic or plasma capture systems. These remain speculative but increasingly plausible within near-future technology. Each incremental improvement brings the idea closer, not just seeing a visitor, but visiting it in return. Atlas leaves behind no artifact, no evidence of origin-only data, interpretation and questions. Yet its impact is measurable in institutional behavior, funding priorities, and collective imagination. It reframed how humanity perceives itself in relation to the broader galaxy. No single observation proved extraordinary claims. But together, the absence of expected phenomena, no tail, no exhaust, no dust taught something subtler, that our definitions of normal cosmic behavior are built on limited experience. The universe is not obliged to fit those expectations. That realization is neither alarming nor mystical. It is a call for precision. Each unexplained measurement now becomes a potential frontier, a reminder that ignorance is not failure, but opportunity. By the end of 2026, the last confirmed light from Atlas had crossed Neptune's orbit, heading into interstellar space at 42.1 kilometers per second. The data archive was sealed and mirrored across 5 research centers to ensure long-term preservation. Every observation, from the earliest amateur image to the final spectroscopic trace, now forms a collective record. A detailed chronicle of a visitor that came uninvited, stayed briefly, and left quietly. The numbers remain unchanged, but their meaning evolves. For astronomers, Atlas is no longer just a data set. It is a milestone, a moment when observation reached beyond habit, when data replaced assumption, and when the universe reminded us once again that discovery begins where certainty ends. Now 3i, Atlas drifts outward, away from the sun and everything that could have studied it more closely. Each day it fades first from telescopes, then from mathematical certainty, until only equations and archived light remain. It carries no message we can read, no signal we can decode. Yet its brief visit has changed how we look beyond our sky. It reminded us that the solar system is not a closed world, but a crossroads, open to travelers from places we cannot yet imagine. Whether a fragment of distant ice or something built with purpose, Atlas has already done its work. It forced questions that reach beyond astronomy, about attention, curiosity, and what we choose to see when evidence challenges comfort. Soon it will be gone, moving silently through interstellar darkness, untouched and unanswering. What remains is our awareness that the void between stars is not empty. It holds visitors, and someday perhaps we will be ready to meet them.